We probably don't know what concavity means. So our objectives today are determine when a function's concave up or concave down. Let's take it one step further. Just know what concavity means. Do you guys know what concavity means when I say concave up or concave down? Was that discussed in pre-calculus? A little bit, Matthew? You're like making a sign with your hands. It's kind of what it is. Yeah, so it's concave up or concave down, and we'll go over that. We're going to find what we call points of inflection, and we're going to learn the second derivative standards, and here we go. So what is concavity? All right, the definition of concavity, which really doesn't help us, but it is good to understand this. Let f be differentiable on an open interval. The graph of f is concave up on our interval when f prime is increasing. I do want you to write that. Concave up, f prime is increasing. Concave down, f prime decreasing. I don't get to today, we'll get through the notes and then we're going to go into graphs. Whatever we don't get to today with all these worksheets, we'll continue and we'll start with on Friday. So I got a lot I'm going to throw at us over the next today, Friday, next week, on Wednesday and Friday. We have another quiz coming up. Did I tell you when the next quiz is? When is it? Is it next? Well, next week we go Tuesday, Wednesday. So it's next Wednesday? Woo! Man, hope you guys are ready. All right, good luck. All right, so here we go. All right, so what's concave up? Here's what it looks like. I would always tell students if I poured water on the graph, it would roll down into the cup. So the definition, though, is when the tangent lines are below the original graph, it's concave up. So when the tangent lines are below, this is the graph of f. That's concave up. And then look, concave down. I always tell students if I would pour water onto the graph, it would roll off. When the tangent lines are above, it's concave down. Okay. You guys are all tired. They stay up too late. So thankful. All right. Look at this now. Back to our math. Let's TikTok this out. Let's get a million hits. All right. Yeah. So here's my graph. Just look at it. Nothing to write. Does everybody see how this is concave down to here? Then it changes to concave up. Can you all follow that? Do you see how every tangent line's above it, and then all of a sudden the tangent lines go below it? Can you follow that? So first of all, you don't need to write down yet. Where the concavity changes, that's known as your point of inflection. Okay? So that's concave down, that's concave up. Now look here. This is the graph, this is the derivative of this. Okay? Look at this. This derivative is decreasing. This function was concave down. Didn't we say that's the definition? The derivative here is increasing, concave up. Okay? You're going, so what? Well, that means this. And this is the test for concavity. If the second derivative, look up here before you write it. What's that mean? Second derivative greater than 0. If the second derivative is positive, the graph is concave up. If the second derivative is negative, that means concave down. Back up for a second before you write it down. Look here, look here, look here. This is the first derivative, right? Now, I'm asking you to think of the tangent lines. So what's the tangent of the first derivative? That would be the second derivative. Aren't all these tangent lines negative? Concave down. Aren't all these tangent lines positive? Concave up. That's where we get the test for concavity. So write it down. All right. So I'm not going to write it out. Let's just talk about it. Determine the open intervals in which this function is concave up or concave down. So you know what I'm going to do? I'm going to take the first derivative. Then I'm going to take the second derivative. And I'm going to find my zeros of the second derivative. And my zeros are at -1 and 1. Okay? Just look here. Then I'm going to pick a test point. So look. Here, a test point between -50 and -1, the second derivative is positive. That means my original graph was concave up. The second derivative is negative. That means concave down. The second derivative is positive. That means concave up. So like last class we tested for when's our function increasing or decreasing by the first derivative. Today we can look at the second derivative and tell me concavity. Okay. All right. Points of inflection. The definition of point of inflection is simply where concavity changes. So notice here, guys, look up on the picture. This was concave up, then concave down. That's a point of inflection. This was concave down. Now it's concave up. That's a point of inflection. So just like we could do with the first derivative test, we could determine relative max and mins where it change from increasing to decreasing. We can change for points of inflection where the concavity changes. Questions for me? So there's three types of points of inflection. Concave up to concave down. Look at this one. Concave down to concave up. Look at this one. It's concave up, concave down. So this one, you have a tangent line. Here you have a tangent that's 0, and here you have a tangent that's undefined. Okay? But the concavity changed. So, points of inflection, if C comma f of C is a point of inflection, then we should know this. The second derivative had to be 0, or the second derivative does not exist. So point of inflection is where concavity changes, but we also know the second point of inflection, the second derivative had to either be 0 or undefined, does not exist. You doing okay still? The last thing I want to talk to you guys about today is, this is just showing you how you determine, I just did one like this, so you just check it and then you do test points to do it. So that's just what I just showed, right? So then I want to talk to you about, this is good too. Let's talk about this. This is, look at this one. The second derivative is 0, but still the concavity didn't change. So we know points of inflection the second derivative is always 0, but just because the second derivative is 0 does not guarantee it's a point of inflection. We also have to make sure, verify, did the concavity change? Okay, did the concavity change? Second derivative test, I really like this one. Okay? Here's what I know. If the graph of a function is concave down, right? So the first derivative was 0. And if the second derivative at that value, c, so that's a relative, everybody agree that's a relative maximum point? Okay? So the first derivative would be 0. But the second derivative at c would give me negative. Then I have a relative max. Come over here. This is concave up. This is a relative what? Min. The first derivative would be a horizontal tangent. Agree? The second derivative would be positive. Why? Because it's concave what? If the first derivative is 0 and the second derivative is positive, it's a relative maximum. That's the second derivative test. So write it down. This is important that you first state this. Let f be a function such that the first derivative at c is 0. So we got to have the first derivative equal to 0. Then we can conclude this. If the second derivative of that c value is positive, and I always tell students to think this, if the second derivative is positive, I have a relative min. If the second derivative is negative, I have a relative max. We're going to use this a ton, the second derivative test, when we talk about optimization here later on this unit. Okay. All right, I'm moving on. So I'm going to go through this real quick because I want to get to the graphs today. So I say find the relative extrema using the second derivative test. So I set the first derivative equal to 0, and I find my zeros. So when we look at this, we'd have zeros at -1, 0, and 1. Okay? Then, listen, all we do is plug -1 into the second derivative. So I find the second derivative. I plug those values in. -1 is positive. Therefore, it was a relative minimum. Come over here. At the second derivative of 1 was negative. Therefore, it was a relative max. Now, notice this one in the middle. The second derivative of 0 was not either positive or negative. It actually told me 0. So the second derivative test failed, which meant I didn't have a relative max or min. Okay? So let's do this. Get this up here. Whoop. There's your homework assignment. Get a picture of it. And then I want to get out. We got all kinds of stuff. We're gonna work to the bell rings of worksheets here. Can y'all look at me? Can you find the worksheet I gave you last time that looks like this? It was in the group of worksheets I gave you last time. Going away from the homework, so take a snapshot of it. We'll do it on Canvas later. Okay? Here we go. I want this worksheet. I need my new technology back. Look how hard it is to see that compared to the old TV monitor. Do you guys like the TV monitor? Yeah.
Could you see it okay?
Except for what? Your sight. So let's all find this one. So just heads up now. So I've given you the definition to all this. Because I told you guys on the AP exam and on the IU final exam, we do a ton of interpretation by looking at tables and graphs, and those graphs tell us things about the original function. Okay, I've given you the analytical. Now we got to interpret it from the different aspects of the function. So that's what we're going to do right here. This is going to help us. This one's pretty straightforward. We're just going to make sure we have our vocab. When I say find the roots of f of x, what's that mean? Find the, what's another word for root? zeros, x-intercepts, solutions. So look at that graph. Our roots occur where? At A, where else? C, G, and K. Okay? Points of discontinuity. Well, points of discontinuity, let's just do the simple thing. Our graph's not continuous. We have to pick up our pencil. I think we only have one point of discontinuity, and that point of discontinuity is the vertical asymptote at where? H. So X, the point of discontinuity is at H. Okay. Critical points. What's the definition of a critical number? Where the derivative is 0 or undefined. So let's look at this graph and go, where would I have a horizontal tangent or undefined tangent? Why is B a critical point? A what? Sharp turn. So it's undefined. Where else? Let's go along this curve. Right here at D, why? Yep, 0. The derivative is 0, so at D. Where else? Here at F. Derivative is 0. Where else? Hey, this is undefined. This is undefined. Would you all agree? So critical point at H. Now, look at this. From H to I, all the x values between H and I are a critical number. So I would write that as this. I would say all the x values greater than or equal to H, less than or equal to I. That's representing the horizontal tangent right there. Finish it off, see if you can get the rest of them. Hopefully you also said at J, sharp turn, K, horizontal tangent, and M. Agree? With the people you're sitting with, answer D, intervals where F increases. Answer E, intervals which F decreases. F, find the relative max. G, find the absolute max. H, find the relative min. I, find the absolute min. And do J and K, intervals where you have concave up, concave down. Take a few minutes. Take a few minutes. You know what? While we're here, just finish the worksheet. Take a few minutes and then I'll put the answers up there. Talk about it. So where is my function increasing? And then they're intervals, so they're not closed brackets, they're parentheses.
Where? Yeah, did I not? Oh, it's still continuous.
It's just not differential.
I just remembered I wasn't here.
Come on up. You spent like 5 minutes. You spent 5 minutes, realized you weren't here on Monday when I passed it out like they're on top.
Julie, has you shoot your technology today by chance?
Today?
She came in her projector.
Oh, you should have printed
Upside
it.
down.
As soon as she hit something.
Her iPad was in green. Like there were multiple things.
Some of it was messing with her.
That's what I said. Some of it's jacking.
It wasn't me. Because I know that's who you look at you like, yeah,
Exactly. If there was a person to do it,
that I would, you're right.
but iPad was in green. That's awesome.
I sent you an email about leaks.
Yeah, I'll go.
I saw it right away. sure you're aware of all of them. Entering the nice entrance, the nice entrance from across from the football stadium into the SAC. Is that the nice new entrance? It's leaking there too. It's new, and you can tell, like, where's that? You can see the stained tile, you can see the stained floor on the carpet. Like the carpet's stained now. I know. We go back to
We have a flat roof, so
understandable.
so anytime
Heavy
we have
downpour.
leaves or anything, there's drains up there, and they run down through the village. Like if you look at Jet Davis, just in the corner, there's just a little box of drywall. Well, it's a real drain. It goes all the way down to the chop. But you get leaves and stuff around it,
It's gonna flood.
it'll flood. So you would think that once a month
November.
we'd have people go out, blow it, whatever.
That one up in Carter. Like tiles have been moved.
Mainly Jim has a leak in the
Where the pipes are.
southwest corner.
I know you know where they are.
West Jim, you can see on the wall.
Just over time. Well, hey, like, we got a locker room in the hottest part of the year. My league's about 8 seasons.
Wait, what's it? Wait, just
Yeah, this is your second person asked this. Only discontinuity is where you have your graph, you have to pick up your pin.
okay, I was thinking.
You're thinking of differentiability. So, you guys need another minute or two? Yes? Okay, that's fine. I'll put this whole thing on the screen. I'll answer it. They're happening. So, you know, buildings, obviously all over the place, though. Some are good, they just need to grow up. Ninth period, it's much more relational. Period, there's some rough kids. It'd be hard to connect with. It's good. I have some because that class is so I gotta win. Right now I gotta win. When I have 19 other kids, I gotta win. Question. Well, you'd have to pick up. So like, this is concave now. That's concave. So this is concave. So that's not a point of question. Concavity and concave. Does that answer your question?
Let me walk you through them. Let me walk you through them. Okay, let me walk you through it. Intervals over which the function's increasing. Okay, I got this. So the interval, let's see if you have the same as me. It's going to, here, I'll write mine, here's mine. I'm saying it's increasing from B to D and from D to F. Now I'm okay if you just, sorry guys, I'm okay if you just said B to F. Why did I break it up? Because I had a 0. So it technically is not increasing at D. It's increasing from B to D, and then again from D to F. So when to be precise, you'd write them as 2 separate. I'm saying it's increasing again from J to K, and then from M out to infinity. Even though this is a horizontal tangent approaching 0, it's still increasing. It's getting closer and closer to 0 without ever reaching. We okay with that one? All right, decreases would be from negative infinity to B,
F to H, I to J, K to M. Questions over those? Okay, to be advantageous with our time, guys, I'm going to pick up our process just slightly. Relative max occur at x equals f. Do you have that one? Now, I think this middle one's really tough. You're going, how is from h to I a relative max? Well, the derivative is 0 everywhere. And before it and after it, there was values smaller. So from h to I, and again at k. Relative minimum, or excuse me, then the absolute max occurs at f. Right? Isn't that the highest point on our graph at f? Okay. Here we go. Relative minimum. I bet you have x equals b. Again, we have to use that constant. I'm not worried about that one. Also, j and m. Do you have b, j, and m? Yes? Absolute minimum? There isn't one. Why? Because I have one approaching negative infinity. I don't have a value. Remember the definition? The only way you're guaranteed an absolute max and absolute min is if your function is continuous everywhere, and that function's not continuous everywhere. That was the extreme value theorem. Okay, continue on. Concave up. You should have D and E, L to M. D to E, L to M. Concave down would be from negative infinity to D, E to H, J to L, M to infinity. I'll give you a second to write those down. Since that's the new stuff, I'm assuming you may be a little inconfident over that. And then I'm just going to reveal the rest. My points of inflection would be at D, E, L, and M. The equation of a horizontal asymptote, there is one, out to the right, y equals 0. The equation of a vertical asymptote is x equals h. I was hoping to get 2 more today. We got plenty of time on Friday. We'll just work through the graphs. Don't forget to approach that homework assignment. Appreciate you guys. Thank you for working hard. If everybody has the quiz taken, we'll go over it on Friday. Chances are there's somebody not going to have the quiz taken.